This video discusses the product rule of differentiation. First, I will write down the product rule. After that, I will prove the product rule. And after that, I will discuss 3 complete examples using the product rule. Here's the product rule. First, I will let y be f times g, where f and g are differentiable functions. Then y prime, which is the derivative of y, should be equal to f times g prime plus f prime times g, where f prime and g prime are the first derivative of f and g respectively. This is called the product rule of differentiation. Whenever you have a product of 2 functions, if you have to differentiate them, the first derivative of that product should be equal to the first function times the derivative of the second function plus the derivative of the first function times the second function. Please note that the product rule of differentiation is a very important property of differentiation, and whenever you have a product of 2 functions, you must use the product rule of differentiation in order to differentiate them. If you do not use the product rule correctly, whenever there is a product of functions to be differentiated, then your answer will definitely be incorrect. Therefore, understanding the product rule is a very important part of calculus. First, we will look at the proof of this theorem. For the proof, I'm going to use the first principles. For those who need to know about the first principles, there's a complete separate video with a complete introduction to the first principles. I'll have the link posted down below. Assuming that you are comfortable with the first principles, I'm going to go ahead and use that and prove this result. Let's begin the proof. I will let h of x to be equal to f of x times g of x. For the first principles, I'm going to use the right-hand differentiability, which means in addition to h of x, I will also need h of x plus delta x. That should be equal to f of x plus delta x times g of x plus delta x. Please note that when I write down h of x equals f of x times g of x, this is the requirement for the product rule. We use the product rule of differentiation in order to differentiate these kinds of products of functions. All right. Now I'm going to go ahead and write down the formula for the first principles. I'm going to use the right-hand differentiability. We know the right-hand differentiability is written as d plus at x equals x. This is equal to limit as delta x approaches to 0. On the numerator, we have h of x plus delta x minus h of x. All of that has to be divided by delta x. I'm going to go ahead and replace h of x plus delta x and h of x in the context of this problem. Then it becomes d plus at x equals x equals limit as delta x approaches to 0. On the numerator, the first term is h of x plus delta x, which is equal to f of x plus delta x times g of x plus delta x. F of x plus delta x times g of x plus delta x. That minus h of x. H of x is equal to f of x times g of x. F of x times g of x. In the denominator, we have a delta x term. Now, if we try the direct substitution of delta x equals 0, as you can see, this first term becomes f of x, the second term becomes g of x. That minus f of x times g of x, the numerator is going to be equal to 0, and that has to be divided by delta x, another 0 in the denominator. Therefore, it's a 0 divided by 0 situation when we do the direct substitution. Therefore, further simplification will be required. To do further simplifications, I'm going to write down this is equal to limit delta x approaches to 0. Let me write down the first part of the numerator as it is for now. F of x plus delta x times g of x plus delta x. With that, I'm going to subtract and add the same quantity for the numerator so that there will be no change. So the term that I'm going to subtract is, I'm going to minus f of x plus delta x times g of x. I need to also go ahead and add that same term onto the numerator so that I haven't changed the given problem. So I will plus f of x plus delta x times g of x. And I should not forget to minus f of x times g of x. So let me write that also down. Minus f of x times g of x. All of that has to be divided by delta x. Now I'm going to focus the first two terms on the numerator. From those first two terms, you can factor out f of x plus delta x. After that, I will focus on the second two terms of the numerator. From those two terms, I can factor out g of x. So let's go ahead and do those two factorings. This is now equal to limit as delta x approaches to 0 on the numerator. From the first part, I'm going to factor out f of x plus delta x. Let me open brackets. Then once I factor out f of x plus delta x from the first two terms, I have g of x plus delta x minus g of x remaining. So let me write down those two. G of x plus delta x minus g of x. Let me close brackets. Now I'm going to look at the second two terms. From those two terms, I'm going to factor out a plus g of x. When I factor out plus g of x, let me open brackets, I will have f of x plus delta x from the first term minus f of x from the second term. Let me go ahead and write those two. F of x plus delta x minus f of x. All of this must be divided by delta x. Now I'm going to split this fraction into two fractions. One fraction will be this part over delta x, and the other fraction is this part over delta x. When I write that down, this limit problem now becomes equal to limit delta x approaches to 0. Let me open big brackets. The first fraction I'm going to write down is f of x plus delta x is outside, and inside brackets we have g of x plus delta x minus g of x. All of that has to be divided by delta x. And then I have this plus sign, and I have a g of x, brackets, I have f of x plus delta x minus f of x, close brackets. All of that has to be divided by delta x again, and close the big brackets. Now, when you look at this term with delta x approaching to 0, what can you say? That is exactly the derivative of g as per the first principles. Similarly, if you look at this part with delta x approaches to 0, that exactly is, according to the first principles, the derivative of the function f. And after that, for the rest, which practically means only this part, we can do the direct substitution of delta x equals 0. Then when we do so, this is going to be equal to, from this one, I have f of x times, we identified all of this part as delta x approaches to 0 as the first derivative of g of x. So let me write that down as g prime x. And then we have this plus sign right here. And then we have the gx right here. gx times, we identified this part as delta x approaches to 0 as the first derivative of f. So let me write it down as that, f prime x. That is the complete proof of the product rule of differentiation. Now we will look at a couple of examples. Here's your first example. You are given y equals 5x cubed sine x. Find dy by dx. To differentiate this function, there is a 5 right here which can be factored out using the second property of differentiation. Using that second property, I'm going to factor out the 5 and write down dy by dx directly as 5 times, let me open brackets. Now I need to differentiate x cubed times sine x. We can see x cubed is a function of x and sine x is another function of x. They are multiplied with each other, therefore I have to use the product rule of differentiation in order to differentiate them. You can identify one of those two functions as f and the other function as g. And then you have to write down first function as it is and differentiate the second, plus the second function as it is and differentiate the first. That's it. Or you may remember it this way. Write down the first function as it is and differentiate the second function. And then write down the second function as it is and differentiate the first function. So let's go ahead and do that. Let me write down the first function as it is, x cubed, and differentiate the second function. Sin x differentiation is equal to cosine x. That plus, write down the second function as it is, which is just sin x, times the derivative of the first function. When you differentiate x cubed, we know it's going to be equal to 3x squared. That 3x squared can be written after this x term also, or before the sin x term. When you write it before the sin x term, it's actually preferred, because when you write it after this x on the right hand side of the sin x, the reader may be confused that the function written there should also be multiplied by the x right here, which is not the case. Therefore, it's advisable that you write down the other components that should be multiplied with sin x term prior to the sin x term. Therefore, let me write down 3x squared right here. Close brackets. This can be seen as a final answer. However, if you like, you can factor out x squared from these two terms. If you do so, dy by dx is going to be equal to 5x squared, open brackets, x times cosine x plus 3 sin x. That's the final answer for that example. Here is your second example. You are given y equals 5x cubed plus 3x squared plus 4x tangent x plus 4 cosine x minus 3. We need to find dy by dx. For this problem, the only product term is x times tangent x. For the other terms, we do not need any product rule. Please note that when you look at the product rule, it should be f times g. It must be a product between two functions rather than a constant times a function. Even if you have a constant times a function, the product rule still works, but it's extremely redundant, wasting time. So whenever you have a constant times a function, you can simply use the second property of differentiation, in which the constant can be taken out and simply differentiate the function. Use the product rule when you have a product of two functions, none of which is equal to a constant. All right, let's go ahead and differentiate this function. Dy by dx should be equal to, the first term is 5x cubed. When I differentiate that, I get 15x squared. That plus the second term is 3x squared. When you differentiate that, you get 6x. That plus, then we have 4x times tangent x. 4 is a constant. Therefore, using the second property of differentiation, I'm going to factor out 4. I will open brackets and then I need to differentiate x times tangent x. When you differentiate x times tangent x, I have to use the product rule. You need to identify x as one function and tangent as the other function. Once you identify those two functions as that, we know the product rule is one function times the derivative of the second function, which is secant squared x in this case, plus the second function, which is tangent x, times the derivative of the first function. When you differentiate x, we know it's going to be equal to just 1. Multiplying tangent x by 1 gives us just tangent x. Therefore, writing 1 is not required. Then we need to differentiate 4 times cosine x. 4 is a constant. You can take that out. And cosine x differentiation is equal to negative sine x. Therefore, that term becomes negative 4 sine x. When you differentiate 3, it becomes 0. Can we do any further simplifications of this? Any further simplifications are not possible because there are no any like terms to be combined. Therefore, we can stop this at this point. That's the final answer for that example. We will look at another example as well. This is your third example. Let's say we have y equals 5 square root x tangent x minus 3x raised to the 4th power. I need to differentiate this function. When I differentiate, I need to identify x times tangent x as a product of two functions. None of them is equal to a constant. Therefore, I must use the product rule. Then dy by dx equals, for the differentiation of that first part of that function, I'm going to factor out a 5 using that second property. I will open brackets and then I need to differentiate square root x times tangent x. I can identify one of them as f, the other function as g, and then simply apply the product rule. One function times the derivative of the other function plus the other function times the derivative of the first function. So differentiation of that part is going to be equal to square root x times the derivative of tangent x is secant squared x plus tangent x times the derivative of square root x. What's the derivative of square root x? Square root x can be seen as x raised to the 1/2 power. When you differentiate that using x to the nth power differentiation, which gives us n times x raised to the n minus 1, that should be equal to 1/2 times x raised to the 1/2 minus 1. Once you simplify that, you get 1/2 times x raised to the negative 1/2, which can be written with positive exponents as 1/2 times 1 over x raised to the 1/2, which simplifies to become 1 over 2 times square root x. Let me close brackets, and now I need to differentiate this last term, 3x to the 4th power. We do not need to use the product rule for 3 times x to the 4th power because 3 is a constant which can be factored out according to the second property of differentiation and simply differentiate x to the 4th. We know the differentiation of x to the 4th is equal to 4 times x to the 3rd. Then that 4 should be multiplied with the 3 right here. It's already minus right here. Therefore, it's going to be minus 12 times x raised to the 3rd power. No further simplifications possible. There are no more like terms to be combined. Therefore, I'm going to stop that at this point. All right, so that's the product rule of differentiation, and we have discussed a couple of examples as well. Thank you so much.